The goals of the Perlan 2 project: exploration, research, and education. We've been trying to inspire kids. For instance, we have a mock-up. This was taken at the Minden Air Show in October. And we let all the kids come set in the mock-up and play fighter pilot. And hopefully one of those is intrigued and ends up studying math, science, or engineering. There's still a couple chairs in the corner that haven't been thrown out.
That's okay.
You know, if you're near the equator, you tend to have easterly winds. If you go to the north or the south, you end up with westerlies. And if you look at South America, for instance, there is a temperate rainforest in the southern part of Chile because the prevailing wind is out of the west. When these prevailing westerlies are strong and zonal, you end up with the Andes causing mountain wave. And if we have a high altitude wind, then the mountain wave will go to high altitude.
Is it warmer or colder, the western or the eastern, or the same?
Well, the temperature really is a function of your latitude. So, you know, up in Brazil, they have their tropical rainforest because the winds are out of the east, pushing up against the Andes, and it dumps all the rain in the tropics. But it's kind of chilly down south. But this is a graphic that shows how the mountain wave is set up. And basically, you have the strong winds coming over the mountains. And if you have stable air, as it comes over the mountains, it tends to come down, but it wants to rebound to the same elevation that it was when it came across the mountains. So the air comes down, and then it rebounds. And in this zone where it rebounds, you can find very strong lift. Many years ago, I was flying a flight out of Cal City and got off tow just north of Mojave. And when my averager first settled down, I was going up 2,800 feet a minute. Wow. Now, when you have that much up, of course, there's that much down somewhere nearby. You get often a rotor cloud in this zone right here. And this morning, out towards the west, there was fantastic rotor clouds. And kind of the hint that it's a rotor cloud caused by a mountain wave. The winds are really strong. If you look closely at the cloud, you can see it forming on the leading edge. Look at the trailing edge, you can see it evaporating. So you have the strong wind and the cloud's not moving. Well, it's forming and dissipating, so it's not the same air, but that's why it stays there. And then you get to higher altitude, the clouds tend to be lens-shaped. We call those lenticular clouds. And again, you've got a strong wind and the cloud is not moving. And a nice rising air along the leading edge. The turbulence in the rotor is the worst turbulence you can imagine. Like flying in your inside your washing machine. The air in the lift zone is the most laminar air you'll ever imagine. Like towing out of Cal City, the tow rope is 200 feet long. You're flying along, you're in this washing machine trying to hang on, and all of a sudden the tow plane will start climbing really fast, and 200 feet later, you're on a 200-foot rope, you get in the same air and you transition from the turbulence to the smooth air. And up you go, get off tow and start climbing. Now if you're flying really fast going this way, you can get in trouble. You know, there have been airplanes lost over Mojave because people didn't realize that, and they're flying, you know, above the green arc, and they go into the rotor and break the spars. Okay, so on a wave day, if you're transitioning downwind, you kind of want to be in the green arc. But in the sailplane, where we have low ground speeds and stuff, it's absolutely the smoothest air you can imagine. On our record flight, we flew through turbulence getting to the wave, but once we got off tow, the whole rest of the flight totally smooth, no turbulence. This is a picture taken looking at the South Pole. So this is a graphic of this polar night jet or polar vortex. And basically, in the wintertime at the pole, so that means July through September at the South Pole, you end up with this strong wind at high altitude. A little cross right there is El Calafate. So El Calafate is right at the edge. This was the day of the high flight of the polar vortex. This is a graphic. This is the equator, and this is the South Pole, and this is altitude up to 160,000 feet. So you imagine you got your back to the wind, and this shows the wind speeds. So the subtropical jet, which would be over Brazil, or it's maybe just south of Brazil. It can have good wave, but the wind starts to die off, and then the wave doesn't propagate. And this is typically the jet stream that we have over Minden area or the Sierra when we have good waves. So the wave dies off and get high. But in this case, we're at El Calafate. The polar jet is here. The winds are strong enough to cause a wave, although it's kind of weak on that day. And then we got up into where the strong winds are due to the polar night jet. And potentially we could have climbed higher. This year we took some weather balloons with us, so we got some actual data. Next. And Jackie's pointing out, when he first got there, the Argentines were a little bit reluctant because they do not have air traffic control radar in southern Argentina. They do all of their air traffic control with procedures. So there's many minutes and thousands of feet between airliners that fly around in southern Argentina. Well, you launch a weather balloon, you don't know where it goes. Now in America, there's actually no restrictions on weather balloons, and I've never heard of an airliner or any other airplane hitting a weather balloon, even though they go to high altitude. But we had an intern with us, and he created a website which we called Virtual Balloon Cockpit. And it basically took the telemeter data that came from the balloon, which has GPS location and altitude on it, and we plotted it on a website, so you can see real time where the balloon was. And the very first balloon we launched, they actually delayed us because there was an aircraft operation at an airport 200 kilometers downwind, and they wanted to wait till the airplane was gone before we launched the balloon. But once they saw our virtual balloon cockpit, that kind of resolved their fears, and after that we were freer to launch balloons. And then the other thing, of course, is the balloons always made it to the ocean, so they weren't dropping balloons on their land. But basically, the balloon goes up to. It depends how much helium you put in. The more helium you put in, the faster it goes up, but the lower it bursts. So we're normally putting in enough helium so we get to 100,000 feet or so.
And what's the altitude on? Yeah, that's 102,854.
Yeah.
So it's just over 100,000 when it hits the ocean.
Then it bursts and then it comes down. And you actually get data. It had a parachute on it, so you get data going down. But at that time, it's so far east, the data was not good for us.
They get one of those track forms.
And just to show how strong the winds are at altitude, this was the balloon data from August 4th. And at 105,000 feet, the winds were 205 knots. So we kind of, showed that the winds conform to the theory.
I thought the wind blew in Mojave.
It does.
And on most days, we didn't see winds quite that strong, maybe 160 knots at high altitude, but strong winds a lot. Okay, the Perlan 2. Well, our biggest challenge we've seen so far is the cold temperatures. On the day of our high flight, the lowest temperature we recorded on the outside was minus 90 F.
Wow.
On the inside, there's kind of a huge temperature gradient across the cabin. The lowest we recorded in the cabin was minus 20 C, which is above 0 Fahrenheit. The side towards the sun, of course, is warmer than the downwind side. Remembering that we're pointed west because the wind's out of the west and the sun's in the north, but it's not very high. So the windows on the north side, they tend to stay relatively frost-free. The windows on the shade, forget it, they're going to frost over. On the inside, just from the moisture that comes out of your body. The Perlan itself, as I mentioned, two-seat airplane in tandem, a pressurized cabin. We have a drogue chute in the tail, which is 15 feet in diameter. It's size, so if we have a problem at high altitude, like 90,000 feet, you can put the chute out, and it's supposed to hold you at 80 indicated. So 80 indicated at 90,000 feet is really fast, so you can get down to 50,000 feet in like 4 minutes. We also have a BRS. We decided that the hatch was small enough that if you had a parachute on your back, you couldn't crawl out, especially if the airplane was in some gyration because something had broken. So we have a ballistic recovery chute, which can lower the whole airplane. Otherwise, it's a pretty conventional sailplane. We've got conventional flight control system, fly-by-wire, i.e. cables to the elevator. And we have space in the science bay, we call it, where we've been carrying CubeSats. CubeSat's a little experiments that students build, college students, in our case mainly high school students and even grade school. We got one experiment that was done by I think a first grade class. And we got an air bottle. The pressurization works by having a highly sealed cabin. So we have a leak rate on the order of maybe half a liter a minute or so. And we're just adding air gradually to make up the leak rate so that we keep the pressure where we want it. When we first pressurize, we get 1 psi over the outside pressure. And basically that holds the hatch in. The hatch, we have some latches so it doesn't fall in on you. But those aren't really designed to hold the latch, just the pressure trying to push the hatch out holds the hatch in. And when we get to 14,500, from there on up, the cabin is held at 14,500. And that way, if you had some problem with your oxygen system, you could just take your mask off and breathe the cabin air. We did discover that anything electronic needs to be heated when it gets so cold. We put a camera in the tip of the tail, which actually turned out to be a brilliant move because we've got some fantastic photos. Plus in the cabin we have one more means of seeing out if the windows fog over. And we have flutter exciters in the wingtip. Basically little devices that can vibrate the wingtip. Then we measure how fast the vibrations damp out. And that tells us whether we have a structural problem with the airplane. For those of you in the aerospace business, it's called flutter. And basically, if, say the wings want to bend exactly at 2 hertz, and if the fuselage wants to twist exactly 2 hertz, if you hit a gust that causes the wing to bend at 2 hertz, the fuselage can be excited, and then the two motions can couple on each other, kind of like pushing a kid in the swing at the exact right time. And the vibrations can actually keep getting bigger until something breaks. So we've done ground vibration tests where we had accelerometers all over the airplane. And from the ground vibration tests, we have a computer model of the airplane that predicts how fast the vibrations will damp out at high altitude. And so far, everything has damped out like it's supposed to. So, so we keep climbing up in altitude. Okay, next. This is our flight envelope. So stall speeds at 38, and that may increase a few knots as we go to altitude, just from Reynolds number effects. At sea level, our design VNE is 121 knots, and at 30,000 feet it starts tapering off until you get to 54 knots at 90,000 feet as a VNE. It's kind of interesting because the air is thin. At 90,000 feet you have to go 6.7 times what you'd have to go at sea level to have the same indicated airspeed. So even though our maximum indicated airspeed is 54 knots, if you're actually going that fast up there, you're going over 350 knots true airspeed. And that's how we kind of are able to station keep with strong winds. Okay, Patagonia. So Jackie's going to talk a little bit about, I'll basically give her a travel log.
We're in one of the most pristine and gorgeous areas of this world. So if you have a bucket list and you're looking for someplace to travel, southern Patagonia is absolutely, should go to the top of your bucket list. So El Calafate, and you've seen the big picture, so you know how far south that is. El Calafate is on the shores of Lago Argentina, and it is this glorious milky turquoise color because it is glacier fed. And just north, well, 100 miles north, is a different lake, and it's a different shade of turquoise. So this is pretty authentic as far as what you see. And this entire area has, oh my gosh, 5 huge glaciers and probably 10 medium and, you know, countless small glaciers and or ice field. So it's called Glacier National Park, and it's huge. Like I say, it's 100 miles from here to here, and it's bigger than that. It's just huge. So this is from the north part of it, and this is Mount Fitzroy. This is Cerro Torre, so Tower Hill or Tower Spire. And if this looks faintly familiar to you, the Patagonia Clothing Company has a symbol to represent it. And that's it, baby, right there. Okay, that's it. Actually, I think it cuts off here. It does not include this tower. But this tower, and this was amazing. We were there in September of, this was of 16. That little white glisten is a ice mushroom cap on the top of this tower. So to climb this, and it's one of the 10 hardest climbs on planet Earth, you have to haul all your ice gear with you. You know, do normal climb up this skinny spire there. Then you somehow strap on your crampons or whatever it takes. I'm not a climber, so I don't know. And then you go inverted, and then you climb over the top. And that's how you summit, you know, this thing. Yeah. That one is not on my bucket list. It might be on your bucket list, but not mine. Okay. So, but this area is absolutely peace. So down at the southern lake, this is Perito Moreno Glacier. It is huge. It is 5 miles across, well over 15 miles deep, well over, probably 25, but you know, I don't want to claim what it doesn't have. And the amazing thing about this is it's growing, so the pressure of coming down the valley here pushes it against this hill, Magellan Point, but anyway, pushes it against there. And to give you an idea of scale, this little thin ribbon right here is the wall that goes down into the lake, and it's 70 meters. That's over 200 feet tall. That's what that thin little thing there is. And so this glacier is pushing down because of its weight, and it goes up against the Magellan Point, and the two arms of the lake are then dammed apart from each other. And one of them is still getting more water fed into it, so there grows to be an 80-foot differential between the two arms, which of course creates pressure. And about every 7 years, but sometimes it takes 11 years, it just depends on how, you know, warm and cold the summers and the winters are. So it crams up against here, and then the 80-foot differential pushes underneath, undermines the glacier dam, and water starts flowing through really fast, creates a bridge, because it melts through the dam, and creates a bridge, and then the bridge collapses, and then it starts all over again. We are approximately going into year 5 of one of these cycles. So I've not seen it myself, but man, I intend to. So there's your 200-foot wall, and this is one of the Andean condors, and they are huge birds if they're the full-grown, not the juvenile. And they're, what, 6, maybe 10-foot wingspan? These are big birds. And when we're there, we're not in tourist season, so there's not a whole bunch of people to kind of scare them off. So we get to see them more, whether it's on the ground or in the air. Whereas when you get into the summertime, which is when tourists typically come down to El Calafate, they're a little more scarce. So, of course, I like to visit the glacier. There's a national park there, and we were talking a little bit earlier. You park at the top of Magellan Point, and then you have to hike down, and it is a hike on stairs. So they built new metal stairs that are metal grids, so the snow comes through, so they don't get iced, and you got nice handrails on both sides, and it's steep. My stair climber app on my phone gives me credit for 21 floors when I'm going down, okay? So it's pretty steep, but it's great. So when I was there with Linda Warnock, the guys were working at the hangar, and there wasn't anything for me to do that particular day. I visited, and I absolutely looked at this crevice right here. And, you know, it's 200 feet high, so that's about 120 foot, and I don't know, maybe 40 foot across. So I looked at that particular thing, and then another day we came back, and I knew what to watch. I knew what to watch, and that was on my bucket list, to see the ice coming down. And it goes down so far, this is such a deep valley here, it's going to take a while to finally bounce back up. There it goes. So, I mean, it's 120 by 40 feet. This is as big as a house, okay? It doesn't look like much, but it's as big as a house. All right, so you get to see the condors in the air. We see them on the ground. And there's some other really neat animals in this area. These look a lot like llamas, but like they're called guanacos. Okay, they are not very smart. They jump over fences and get caught on fences all the time, and then they die, and then the condors come down and eat them, and so it's sort of a life cycle there. But I didn't get any close-ups, but they have those big pouty lips and the long eyelashes.
Oh, yes.
Very strange, very, like a camel. Okay, so anyway, that's Guanaco. Here, you see a lot of boulders and one bird. And the bird is like an ostrich, right here. Runs pretty fast. It's called a cohique. Not as tall as what I've seen for ostriches. But if it's moving, it moves fast so you can see it, you can track it. But if it sits down, if it squats, that compared to a boulder, you don't see them. You do not. If they are stationary and they are squatted, you won't see them.